Welcome to the Explainer. I am absolutely thrilled you're here today because we're going to unlock something that sounds, well, incredibly intimidating at first, but is actually beautifully simple. We're tackling an algorithm known as breadth first search. Now look, if you're an absolute beginner and just hearing the word algorithm makes you want to run for the hills, do not worry. We're going to break this all down completely jargon-free, focusing purely on the simple, visual logic that makes it work. By the end of this, you're going to see exactly how this mathematical concept literally powers the digital world all around you.
To get our heads in the right space, let's think about a question you've probably asked yourself while browsing the internet. How do social networks instantly find your second-degree connections? When you log onto a platform and it immediately suggests friends of friends that you might know, how is it doing that so incredibly fast amongst billions of users? It's not magic, right? And the platform definitely isn't guessing. It's actually using a highly specific set of rules to explore that massive web of connections.
And that specific set of rules is exactly what our topic is for today, breadth first search, or BFS for short. Think of BFS as the ultimate solution to our social network question. It's a graph traversal algorithm, which honestly is just a super fancy way of saying it's a systematic search strategy. The defining characteristic of BFS is that it explores all the points at its current distance level completely before it ever moves further away. It just spreads out evenly, step by step. Okay, let's dive into this. Here is our roadmap for the explainer today. 1. The shortest path problem. 2. Exploring floor by floor. 3. How BFS actually works. 4. Real-world applications. And 5. Common algorithm traps.
All right, starting with section 1, the shortest path problem, finding minimum hops. Without a concrete strategy, trying to find a path through a massive network of data is just incredibly inefficient. I mean, you're basically just guessing. So BFS was designed with a few core goals in mind. First, it aims to find the minimum hop routes between points. In what we call an unweighted scenario, where every single jump or connection costs the exact same amount of effort, BFS guarantees you will find the absolute shortest route, no question. Second, it determines connectivity, meaning it figures out which points are actually reachable from your starting location. And third, it processes locations purely by their distance from the start.
Let's move to section 2, exploring floor by floor, level by level traversal. And this brilliant physical metaphor really cements the concept. Imagine you've lost your keys in a massive, multi-story office building. If you're using breadth first search, you're going to search the entire first floor completely. Every single room, every desk on level 1 is fully checked before you even think about walking up the stairs to the second floor. That's BFS. On the flip side, we have the opposite, depth first search, or DFS. That's when you run down a single hallway, take a random staircase, and get completely lost deep in the building without ever checking the rooms right next to the front door. So BFS is that organized, sweeping, floor-by-floor approach.
Section 3. How BFS actually works, the algorithm mechanism.
To make BFS work, we really only need to understand a couple of basic terms. The first is a queue. In the programming world, a queue operates on a first-in, first-out basis. It's literally exactly like waiting in line at a grocery store checkout. The first person to get in the line is the first person to be served and leave the line. This super simple concept is the entire engine that drives our search. The second term is vertices. Now, when you read about algorithms, you're going to see this word absolutely everywhere. But seriously, all you need to know is that vertices are just the connection points. They're intersections on a city map, stops on a subway line, or the individual people in your social network. We're just jumping from one vertex to the next. Let's move forward and see how this actually builds into the algorithm. Honestly, think of it like a simple 5-step baking recipe. Step 1, initialize. We set up a tracker to remember where we've been, and we create our empty grocery store line, our queue. Step 2, start. We mark our starting point is visited, and we put it in the line. Step 3, process. We take whatever is right at the front of the line out. Step 4, explore. We look at all the immediate unvisited neighbors of that point we just took out. We add those neighbors to the back of the line, and crucially, we mark them as visited right then. Step 5, repeat. We just keep looping through this until the line is completely empty. That is it. No intimidating pseudocode required. The reason developers absolutely love this 5-step recipe is how well it manages complexity. In computer science, we talk about time and space complexity. For BFS, the time it takes and the memory space it requires simply scales with the number of stops and connections in your network. It computes that shortest distance incredibly efficiently, relying purely on the number of edges it has to cross.
Okay, section 4, real-world applications, where BFS is used. Now, what's really interesting here is the sheer variety of these applications. I mean, search engines use web crawlers that rely entirely on BFS to explore and map out internet links, level by level. Global network systems use it to analyze the hop distance between different servers just to keep your internet running fast. It's even used in puzzle solving, like those algorithms that solve a Rubik's Cube in the absolute minimum number of moves. And of course, like we mentioned at the very start, social networks use it to pinpoint users within a certain number of connections. They're all powered by that exact same methodical, level-by-level strategy. Finally, Section 5, Common Algorithm Traps. Traps to avoid.
So the crucial point to remember is, standard BFS is brilliant for sure, but it does have a major blind spot. It only works perfectly on unweighted graphs. An unweighted graph is a network where every single move has the exact same cost. But what if you're using a GPS map? One road might be a wide-open highway, while another is totally backed up with a massive traffic jam. The distance or time varies between those stops. That is what we call a weighted graph. Standard BFS does not solve general weighted shortest paths, simply because it assumes every single hop takes the exact same effort.
There are just a few other common traps to be aware of. Remember our grocery store queue, first in, first out? Well, if you accidentally code a stack, which is last in, first out, you instantly change your traversal toward depth first search. You've accidentally turned our beautiful organized floor-by-floor search back into that guy running completely lost down a random hallway. Another trap is marking stops as visited too late. You have to mark vertices as visited the moment they are enqueued, or you're going to end up processing them twice. And finally, you can't assume BFS just magically searches everything. If a graph is actually disconnected, BFS from one starting point will only reach the components it is actively connected to. We've covered the core logic, the real-world uses, and those pesky traps. So I'll leave you with this. The next time you fire up a GPS or you look at your suggested friends online, ask yourself, is the computer searching floor by floor? Understanding breadth-first search completely changes how you see the digital architecture all around you. I really hope this explainer made the complex feel just a little bit simpler for you today. Keep learning, keep questioning, and I will see you in the next explainer.